All right, so we're going to begin sections 13.5 and 13.6 in this video. I'm going to combine the two because they're very closely related. 13.6 and 13.5. The gradient and the directional derivative. So first we'll talk about the gradient. The gradient of a function f at the point x naught, y naught denoted the gradient of f at x naught, y naught. So this symbol, which is called a del, denotes the gradient. So, but we just read this, the gradient of f at x naught, y naught. Is given by the gradient of f at x naught, y naught equals, so it is the vector, the gradient is a vector. Its first component is the partial of f with respect to x at x naught, y naught, and its second component is the partial of f with respect to y at the point x naught, y naught. If f is a function of three variables, the gradient of f at x naught, y naught, z naught is the gradient of f at x naught, y naught, z naught equals the vector whose first component is the partial of f with respect to x evaluated at our point. Second component is the partial of f with respect to y evaluated at the point. And the third component is the partial of f with respect to z evaluated at the point x naught, y naught, z naught. Recall that f sub x and f sub y are the rates of change of f of x, y in the directions of x and y respectively. So we already know how to find the rate of change if we want to go, if we're traveling on some surface or some in the x direction, or if we're traveling on the surface in the y direction. But what if we're not traveling in the x direction or the y direction? Then in that scenario, we'll need a directional derivative to find the rate of change. So the directional derivative of f at the point x naught, y naught in the direction of a unit, and underline unit twice because you have to have a unit vector u, which we'll say has components a1 and a2, denoted d sub u of f at x naught, y naught is, and you can also just read this as the directional derivative of f in the direction of u, evaluated at x naught, y naught, or just d sub u of f at x naught, y naught, excuse me. So this is, how do we compute this? The directional derivative of f in the direction of u at x naught, y naught is equal to the partial of f with respect to x evaluated at x naught, y naught times a1 plus the partial derivative of f with respect to y evaluated at x naught, y naught times a2. Now this can be rewritten as the gradient vector of f at x naught, y naught dotted with the unit vector u. So this is why I just teach these two concepts together, because the directional derivative is just the gradient vector dotted with the unit vector. So now that we know how to do the gradient, we can just look at this directional derivative in this form. Now let me sketch. What I'll do is I'll sketch the same way I sketched f sub x and f sub y. I'm going to sketch what we're getting here, give you an intuitive idea of what we're getting when we do the directional derivative. And we'll sketch that same figure that we used for the partial of f with respect to x and the partial of f with respect to y. So we had something that looked like this, where we have some surface, some curved surface here. Now, before, when we held x constant, if we held x constant, so if I were like on some plane that was parallel to the y-axis, meaning I'm holding x constant, then we're taking, we would be looking at f sub y. If I were to hold y constant, so I had some plane that was coming out this way and I sliced through this surface with that plane, then in that scenario, when we held y constant, we were looking at f sub x. But now, say for instance, we look at a plane that is neither parallel to the x-axis nor the y-axis. So say we have, we want to come in this direction. So now that will make a curve that kind of comes out that way. So we take a plane, we slice through this surface with a plane that's in that slanted direction. So first, this will be our vector u. And remember, u has to be a unit vector. So that's why I didn't extend this vector all the way to here. I mean, of course, I don't know how long that dotted line was anyway, but that would be our unit vector. So now instead of traveling in the y direction with our x being held constant, or traveling in the x direction with our y being held constant, we can travel in any direction we want to. So it doesn't matter which direction. And then we can still find the rate of change. So say we had a point right here. I want the slope of the tangent line at that point is given by the directional derivative. So the directional derivative will give us the rate of change in the function as we travel in the direction of this unit vector right there. All right, so now let's look at some other things that we can get from using the directional derivative. Oh, actually, let me write down what I just had. So that d sub u of f at x naught. So rate of change of f of x y at point x naught y naught in the direction of u. All right. So now, what else can we use, or what else can we get from that directional derivative? So the maximum value of the directional derivative in the direction of u of f at x naught y naught is the length of the vector so the length of the gradient at f of x naught y naught. So that's the maximum value that you're going to get for this. That at x naught y naught and let me write this a little bit differently so it's less confusing. And f increases most rapidly in the direction of the gradient vector of f at x naught y naught at x naught y naught. So I keep putting this at x naught y naught because if I want the maximum value of the directional derivative at that point, I have to take the length of this vector at that point. So that only gives the maximum value at that particular point. It doesn't give the maximum value in general. It just gives the maximum value there. So that's basically, if you can think of it as if I were on this surface and I wanted to figure out which way to go from this particular point, and this point right here, sorry, let me slide it down. This point right here is, now bear in mind I have this unit vector. So I'm on a plane that slices through the surface right through that unit vector right there, and I'm also at this point x naught y naught. So there are two things that are at play here. So, well, a few more than two, but you have your surface, which is f of x y z, you have the direction that you want to travel, and then you have the point where you are currently standing on that surface. So if you want the maximum value or the maximum rate of change, so you want it to get to the top fastest on that point, but you have to travel in the direction of this unit vector, then um, you would travel in the direction of the gradient vector. That's the direction you would travel. And what would the rate at which you're traveling be? It would be the length of the gradient vector. So in this scenario, it would tell me, okay, so I go travel this way. If I want to know what is this, this is going to be, that direction is the direction of this. And then also how fast am I going? That will be given by that. So, but all of that is specific to this point. So if I move to like this point down here, for instance, or a point down there, for instance, you use the same material, but you're going to get different values. So those values that you get are very specific to the point that you're considering. All right. So now I talked about all of this in terms of two variables, but we can also consider the same stuff with a function of three variables. So analogous results hold for a function of three variables. All right. So another thing that relates to the gradient is the tangent plane. So given a level surface, and don't worry too much about the definition of level surface. It's mentioned in your textbook. I didn't talk about it because we're not going to be too concerned with it, but it's just going to be where you have your function is a function of three variables and is set equal to a constant. So given a level surface, f of x, y, z equals c. So you don't need to know that name. You just need to know this. The equation of the tangent plane to f at x naught, y naught, z naught is, and I'm not going to have space to fit this on one line, but you all should if you can, f sub x at x naught, y naught, z naught times x minus x naught plus f sub y at x naught, y naught, z naught times y minus y naught plus f sub z at x naught, y naught, z naught times z minus z naught equals 0. So this equation of a plane, of course, is not new to you all. The only thing that we've changed here is now we have our normal vector is given by the gradient vector. So notice the normal vector, that would be the first component, the second component, third component. The normal vector in this scenario is going to be your gradient vector to find the equation of a tangent plane. So now that's for a function of three variables. So for instance, that would work for a sphere. If we were looking at a sphere, well, not a function of three variables equals a constant, sorry. So the equation of a sphere, that would work to find a tangent plane for something like that. So now keeping that in mind, so thus viewing the function z equals f of xy as the level surface f of xy minus z equals 0. So we're just subtracting z from both sides here. And now we have a function of x, y, and z equals 0. So now we can just use that exact same formula that we had on the previous page. The equation of the tangent plane to the graph of f at the point x naught, y naught is the partial of f with respect to x at x naught, y naught times x minus x naught plus the partial of f with respect to y at x naught, y naught times y minus y naught. And then that formula set plus the partial of f with respect to z. The partial, but now we're looking at the partial of this thing. So it's not really the partial of the f. So if we took the partial of this thing with respect to x and y, or if we did it with respect to x, excuse me, we would just get the partial of that part with respect to x. So right here, you could look at this and say, okay, I'm taking the partial of this entire thing with respect to x. That part is going to be 0. So it just boils down to being this. The partial of this entire thing with respect to y, that still boils down to being 0. So it just turns out to be this. Now the partial of this entire thing with respect to z is just -1. So that last term is going to be -1 times z minus z naught, and then that equals 0. Now x naught and y naught we're given right here. What is z naught? Z naught is just f of x naught, y naught. So where z naught is equal to f of x naught, y naught. All right, so I'll stop this video here, and I think we have all of the information that we need to now start doing some problems from sections 13.5 and 13.6.